Good day, everyone. So the lecture that we have for now is lipid metabolism. This lecture is divided into two parts. The first part will be dealing with the review of lipoprotein transport and metabolism. And then we shall be continuing with the second part, where we shall discuss fatty acid oxidation and synthesis. And the lecture on lipid metabolism will end with the third part, where we shall now focus on cholesterol metabolism. So now let's start with lipoprotein transport and metabolism. For this part, we shall have a brief review of the structure of lipoprotein, but we shall be mainly focusing on the function, the transport, and the metabolism of chylomicron, VLDL, LDL, and HDL. We will also have a brief clinical correlation to put your knowledge into use. So what are lipoproteins first? So we all know that these are clusters of lipids and proteins, and that they are used as transport vehicles for lipids or fats, so that these lipids and fats can be transported from one body part into another. Like what I have mentioned earlier, the different lipoproteins are chylomicron, very low density lipoproteins, low density lipoproteins, and high density lipoproteins. The typical composition of a lipoprotein is illustrated here. In its core, you will find the most hydrophobic of all lipids. This would include triglycerides and cholesterol esters in varying proportion depending on the type of lipoprotein. Now, lipoprotein is covered by a single layer of phospholipid, and embedded on the phospholipid are the apoproteins. The different apoproteins, of course, vary according to the type of lipoproteins. Let's compare now the relative sizes of the different lipoproteins. So we all know that chylomicron is the largest, whereas HDL is the smallest. But there is a reason for that. If we compare now the relative composition of the different lipoproteins. So chylomicron is the largest, but it is the least dense. This is because it is predominantly composed of triglycerides with relatively fewer proteins. In contrast, the smallest and the most dense is HDL because it contains a lot of proteins relative to the amount of triglycerides and other lipids it contains. In terms of composition, what comes close to chylomicron would be VLDL, in that they are predominantly composed of triglyceride. The difference, however, is that chylomicron carries exogenous or dietary triglycerides and lipids, whereas VLDL carries endogenous triglycerides and other lipids, such as cholesterol. If we take out the triglyceride in VLDL, what you have now is its derivative, known as LDL. So in other words, LDL is nothing more than a VLDL where the triglycerides have been taken out. So the first member of the lipoprotein family that we shall be discussing today is the chylomicron. Chylomicron is produced in the small intestine. What is the reason for that? Its function is really to carry dietary lipids, such as triglyceride and some cholesterol, to different body tissues, such as the skeletal muscle, the cardiac muscle, and of course, the adipose tissue. And just like what we have reviewed earlier, it's covered by phospholipid membrane, and embedded on it are the different apoproteins, namely ApoB48, ApoA, ApoE, and ApoC. So in this schematic diagram, we can see now the structure of a chylomicron. In its core, you will find dietary triglycerides predominantly, and some cholesterol. Embedded on the phospholipid membrane are apoproteins such as ApoB. Now, these are the ones that are initially acquired in the small intestine together with ApoA. In circulation, it will eventually acquire ApoE as well as ApoC. So let's take a look at the formation now of chylomicron. So the triglycerides, excuse me, have to be hydrolyzed to fatty acids and monoglycerides before they can be absorbed in the intestinal epithelium. Once inside the intestinal epithelium, the triglycerides are reassembled back, and inside endoplasmic reticulum, they're packaged now as a chylomicron together with the other apoproteins. And it is eventually exocytosed into a lymphatic vessel. So as you can see, chylomicrons are not secreted directly into the bloodstream, but rather they enter the lymphatic circulation first before entering the bloodstream via the left subclavian vein. So what are the main features now of chylomicron metabolism? So we did already mention that they are packages of dietary fat, predominantly triglycerides. They are synthesized in the small intestine, secreted into the lymphatics rather than directly into the bloodstream. The initial apoproteins are ApoB48 and ApoA. And in circulation, chylomicron will acquire ApoE and ApoC. Now on the target tissue, a chylomicron will be acted upon by the enzyme called lipoprotein lipase, found in adipose and muscle capillaries. When its content has been unloaded, what you have now is a chylomicron remnant, which eventually will be taken up and catabolized by the liver, as illustrated here. So this is a simple diagram illustrating the fate of chylomicron. So like what we have said earlier, it is produced in the small intestine, secreted initially into the lymphatics before reaching the general circulation. And it delivers its fatty acid content to three main tissues, namely adipocytes for storage and muscles such as the heart and skeletal muscle, so that those fatty acids can be used as metabolic fuel. Once it has unloaded its content, what you have now is a remnant which eventually travels into the liver and is catabolized in the liver. The complete life story of a chylomicron is illustrated here. The half-life of a chylomicron is rather short. It's only the half-life is lasting from 5 to 10 minutes. And as the illustration shows here, it starts in the small intestine, delivers its contents to muscles such as skeletal, cardiac, and adipose tissue. And the final destination where it will be catabolized is the liver. Let's take out the elements first so that we have a simple diagram. So let's start from the beginning. So dietary lipids are packaged as nascent chylomicron, and it is initially secreted into the lymphatics before reaching the circulation. It only contains initially ApoB48 and ApoA. Once reaching the circulation, it will encounter HDL. ApoE, as well as ApoC, actually comes from HDL. Now what you have is a mature chylomicron, ready to deliver its fatty acid content to the target tissue. And like what we have said earlier, the target tissues includes muscle, both cardiac and skeletal. Only skeletal muscle is shown here, as well as adipose tissue. ApoC is important because it activates the enzyme lipoprotein lipase, which hydrolyzes the triglyceride into fatty acid, which is taken up by those target tissue, either to be used as metabolic fuel in the muscle or stored in the adipose tissue. Glycerol travels somewhere else we shall discuss the fate of glycerol in a little while. Once it has unloaded most of its content, ApoC is eventually returned back to HDL. This now prevents the chylomicron from further unloading its content. What you have is called a chylomicron remnant. Now, since chylomicron remnant still contains ApoE, it can be recognized by the liver by binding to an ApoE receptor. So its final destination is the liver, where it is eventually catabolized. What about glycerol? Let's discuss now the fate of glycerol. After the release from chylomicron and VLDL, as you will see later on, it is taken up by two organs, namely the liver and kidney, where, as you can see in this illustration, glycerol is converted into dihydroxyacetone phosphate, an intermediate in glycolysis, as well as gluconeogenesis. So glycerol actually participates in glycolysis and gluconeogenesis in the liver and in the kidney. What about ApoC? ApoC also plays an important role because ApoC activates the enzyme lipoprotein lipase. In this illustration, on the target tissue, particularly on the endothelial lining of the adipose tissue, we can see that the enzyme lipoprotein lipase is anchored into the cell membrane by a short oligosaccharide chain. By itself, it is inactive. It requires the presence of ApoC to have the fully active enzyme. So when ApoC is bind to lipoprotein lipase, that's the only time that the lipoprotein lipase will hydrolyze the content of the lipoprotein chylomicron. Thus, when ApoC is returned back to HDL, this now prevents the lipoprotein lipase from further degrading a chylomicron. Let's recap now the metabolism of chylomicron. So we all know that it is produced or assembled in the intestinal mucosa. Its function is to transport exogenous lipids such as fatty acids to adipose tissue and muscle such as skeletal as well as cardiac muscle. The initial apoproteins are ApoB48 and ApoA, initially secreted into the lymphatics but eventually will enter the circulation via the left subclavian vein. Now, in circulation, it will acquire ApoC2 and ApoE from HDL. In the capillaries of adipose tissue and muscle, fatty acids are hydrolyzed by the enzyme lipoprotein lipase. ApoC2 activates lipoprotein lipase. Now, the free fatty acids are absorbed by these target tissues, whereas glycerol is returned to the liver and kidneys for gluconeogenesis or glycolysis. So during the removal of the free fatty acids, ApoA and ApoC are ultimately returned to HDL. With the loss of ApoC2, this now prevents the lipoprotein lipase from further degrading the chylomicron. And what you have now is the chylomicron remnant, which eventually is taken up by the liver. Now, in the liver, recognition of the chylomicron remnant requires ApoE, and thus the chylomicron remnant binds to an ApoE receptor in the liver. Now, let's move on to the metabolism of VLDL. There's actually a lot of similarities between the metabolism of chylomicron and that of VLDL. The only difference, one of the major differences, however, is that VLDL is synthesized in the liver rather than in the small intestine. Well, just like a chylomicron, it predominantly contains liver triglycerides or endogenous triglycerides rather than dietary triglycerides, and some cholesterol, of course. Just like a chylomicron, it is also covered by a phospholipid membrane, and embedded on it are ApoB100. Now, this is actually the larger version of ApoB48. And in circulation later on, it will acquire ApoE and ApoC, just like what happened to chylomicron. And I'm sure you can guess by now that ApoE and ApoC actually comes from HDL. So looking now at the schematic diagram of the structure of VLDL. So we all know that in its core, you would find endogenous triglycerides and some cholesterol, and embedded on the membrane are ApoB100, acquired in the liver. And in circulation, it will eventually acquire ApoE as well as ApoC. Let's briefly compare VLDL versus chylomicron. They do have a lot of similarities. And of course, there are some differences. One of the differences is that chylomicron is produced in the small intestine, whereas VLDL is produced in the liver. What about the similarities? Well, both of them are predominantly composed of triglycerides. However, the triglycerides in VLDL are endogenous, whereas the triglycerides in chylomicron are dietary or exogenous. Now, even their apoproteins are virtually similar. We have the smaller version on the liver, on the chylomicron. It is called ApoB48 because it only contains 48% of the molecular weight of ApoB100, which is the full-length enzyme. They also have the same function in that they will deliver their fatty acid content to exactly the same target tissues, and that would be skeletal muscle as well as adipocyte. Now, it is in the ending where the fates become a little bit different. We all know that the chylomicron remnant eventually ends up in the liver, whereas for VLDL, there are two possibilities. One is that just like a chylomicron remnant, it can also end up in the liver, or it can give rise to LDL. So now let's take a look at the metabolism of VLDL. So it starts in the liver, enters the circulation directly, delivers its fatty acid to skeletal cardiac muscles, as well as adipose tissue. And the ending is that one possible ending is similar to chylomicron remnant. It will be taken up by the liver. So let's discuss now the metabolism of VLDL step by step. So the liver produces endogenous lipids from excess calories, such as excess carbohydrate, excess lipids, and excess proteins. Now, these lipids do not stay in the liver forever, but they have to be exported out so that they can be used for metabolic fuel or can be stored by adipose tissue. And those lipids eventually are exported out in the form of VLDL, initially a nascent VLDL, directly into the circulation. In circulation, the nascent VLDL will acquire ApoE and ApoC, becoming now the mature VLDL. ApoC is once more important because it activates the enzyme lipoprotein lipase, which hydrolyzes the triglyceride into fatty acid, which is taken up by those target tissues, and the glycerol, which, as we know, travels into the liver and kidney for either gluconeogenesis or glycolysis. When ApoC is ultimately returned to HDL, this now prevents the VLDL from further unloading its content. And what is left behind is what is referred to as the IDL, intermediate density lipoprotein, or the VLDL remnant. What happens now to the VLDL remnant? Well, as long as it contains ApoE, it can be recognized by the liver. It can be returned to the liver and can be catabolized by the liver. So that is one possible fate for a VLDL remnant. However, if it loses ApoE, VLDL remnant cannot return to the liver, cannot be taken up by the hepatocyte right away, but rather it will be acted by an enzyme called hepatic lipase. Now, this hepatic lipase will take out most of the remaining triglycerides. And what is going to be left behind are predominantly cholesterol, thus converting the VLDL remnant into LDL, a lipoprotein that is rich in cholesterol. Let's recap VLDL catabolism. So excess fat, excess carbohydrate, as well as excess proteins are converted into triglycerides and cholesterol in the liver. This won't stay in the liver forever, but rather they are packaged into VLDL and released into the circulation for delivery to muscles and adipose tissue. So in other words, VLDL transports endogenously derived triglycerides to extrahepatic tissues. So the nascent VLDL in circulation acquires ApoC and ApoE from circulating HDL. Now, lipoprotein lipase hydrolyzes the triglyceride. ApoC is eventually returned to HDL, converting now VLDL to IDL or the VLDL remnant. Now, the remaining proteins are ApoB100 as well as ApoE. What are the fates now of IDL? One possible fate is that it can be converted into LDL, or it can be taken up directly by the liver. So the conversion of IDL to LDL occurs as more triglycerides are taken out by the enzyme hepatic lipase. So IDL requires both ApoB100 or ApoE for interaction with either an ApoB100 or an ApoE receptor in the liver. So this illustration now shows the fate of both VLDL and LDL. So we all know that excess calories are converted into lipids in the liver, exported out in the form of VLDL. Once it has delivered its content, it is converted into IDL. As long as it contains ApoE, IDL can return to the liver and be catabolized there. However, if it loses ApoE, it will not be taken up by the liver directly right away, but rather it will be acted upon by the enzyme referred to as hepatic lipase, which takes out most of the remaining triglycerides, leaving only behind cholesterol, converting IDL to LDL. Well, the LDL can still return to the liver. 75% of that returns to the liver by binding to another receptor called the ApoB100 receptor, as we shall be discussing in a little while. Whereas the remaining 24% delivers those cholesterol to peripheral tissue by binding to ApoB100 receptors in a process referred to as receptor-mediated endocytosis. Let's now discuss the catabolism of LDL. This is going to be very easy because we already know where it came from, and we have already mentioned its possible fate. So LDL is the primary plasma carrier of cholesterol for delivery to all tissues. The exclusive apolipoprotein is now ApoB100. So it delivers its cholesterol to different tissues, mainly via a mechanism called LDL receptor-mediated endocytosis, which requires recognition of ApoB100. And where is this LDL receptor-mediated endocytosis taking place? 75% happen in the liver, whereas the remaining 24% occur in peripheral tissues that require cholesterol, such as adrenal glands and adipose tissue. So in this illustration, we can see that IDL can either return to the liver or be converted into LDL when it loses ApoE and acted upon by hepatic lipase. What happens now to LDL? 75% of LDL can be taken up by the liver through a mechanism called LDL receptor-mediated endocytosis that requires recognition of ApoB100. 24% delivers cholesterol to peripheral tissue, again through the same mechanism, LDL receptor-mediated endocytosis. 1% delivers their cholesterol to macrophages through the same mechanism, still LDL receptor-mediated endocytosis. It is actually those macrophages that have engulfed LDL that will ultimately give rise to the foam cells that initiates the cascade that results in the formation of atherosclerosis. So what is this receptor-mediated endocytosis? So all those organs that we have mentioned contain an LDL receptor that recognizes ApoB100 found on LDL. Let's start from the beginning. So ApoB100 on LDL binds to the LDL receptors found on the cell membrane surface of the main organs that we have mentioned. Once bound, it is endocytosed, forming now an endosome. The environment within the endosome is very acidic. The pH is low. This causes the ApoB100 to dissociate from the receptor, and the receptor is recycled back to the surface. The endosome eventually fuses with a lysosome, which naturally we know contains a lot of lytic and digestive enzymes. So the ApoB100, as well as the entire LDL, is digested, causing now the release of cholesterol, which can be used by the tissue or the cell for different purposes. It can serve as a precursor for the production of hormones, steroid hormones to be exact. So let's recap. Receptor-mediated endocytosis of LDL occurs in the liver, as well as in tissues that require a lot of cholesterol, such as adrenal and adipose tissue. So the endocytosed vesicles fuse with lysosome. The endosome itself contains ATP-dependent proton pumps, which lower the pH within the endosome. This results in the dissociation of LDL from the receptor. Receptors are recycled to plasma membrane. Lysosomes degrade the apoproteins, releasing now the cholesterol, which are hydrolyzed to yield free cholesterol, which can be used by those cells for whatever purpose, such as production of steroid hormone. So how is the plasma LDL production and uptake by the liver controlled? Let's discuss first the normal pathway that we have already discussed earlier. So those excess carbohydrates, proteins, and lipids are packaged in the liver in the form of the LDL, exported out, delivers the free fatty acids to the target tissue. IDL returns to the liver by binding to ApoE receptor, or when converted into LDL, can be taken up by the liver by binding to ApoB100 receptor in a mechanism called LDL receptor-mediated endocytosis. However, if there's excessive levels of lipids, such as cholesterol, in the liver, this causes repression of LDL receptor synthesis. So there's downregulation now of both ApoE receptor as well as ApoB100 receptor. With the downregulation of those receptors, IDL cannot be taken up directly by the liver yet. So instead, it will be converted into LDL. Now, since there's also downregulation of ApoB100 receptors, LDL cannot return to the liver right away. So this causes now an elevation in circulating LDL, which unfortunately will deposit its cholesterol to peripheral tissues, such as the ones that we have mentioned, including the macrophages found in artery wall. This now initiates the formation of atherosclerosis. So in other words, a diet that is in excessive, that contains a lot of calories can result in elevation of both VLDL and LDL. So the bottom line, a diet that contains a lot of calories can put you at risk for the development of atherosclerosis. For this particular reason, the downregulation of both ApoB100 and ApoE receptors in the liver. There are, of course, some individuals who have genetic defect in the production of both hepatic ApoE receptor and ApoB100 receptors in the liver. So even with normal levels of lipids in the liver does not produce these particular receptors. As a consequence, IDL cannot return, right away converted into LDL, which also cannot be returned to the liver. So again, it delivers its triglycerides and cholesterol to different tissue. This would now put the person at risk for the development of atherosclerosis, even at a very young age. So this disorder is a result of genetic defect in LDL receptor gene that encodes for ApoB100 and ApoE receptor. Let me correct that, ApoB100 receptors in the liver and ApoE receptors in the liver as well. The mutation occurs in 1 in 500 individuals for heterozygous mutation. And for homozygous mutation, it can occur in 1 in 1 million individuals. Now, even with heterozygous mutation, that is enough to cause symptoms such as elevated cholesterol, primarily LDL. Now, those LDLs are phagocytosed by macrophages, resulting to xanthomas and atherosclerosis. One of the symptoms and signs of familial hypercholesterolemia is the presence of xanthomas on the skin, indicating high levels of circulating LDL. So what is our LDL target level now? Well, with lower LDL cholesterol, the better it would be for the patient's health. So anything less than 100 milligram per DL is the optimal value. And as we go higher in the value, the risk for the development of coronary heart disease and atherosclerosis also increases. So finally, let's move on to the metabolism of HDL. Now, HDL is composed of heterogeneous population of lipoprotein. And why do we say heterogeneous? There's a wide variation in terms of size, in terms of protein content, and lipid composition. Well, the major function of HDL is to transport peripheral tissue cholesterol back to the liver for catabolism, a process we call the reverse cholesterol transport. Because of this function, HDL has a major atheroprotective function. It also has anti-inflammatory, antioxidant, and vasodilatory effect. So in other words, it really protects a person from the risk of coronary heart disease. The catabolism of HDL is summarized in this illustration. There are 2 organs that produces HDL, namely the small intestine as well as the liver. HDL is initially secreted in the form of a protein, ApoA1, devoid of any cholesterol or any other lipids. Now, eventually, It picks up cholesterol from other circulating HDL. And once it's now a pre-beta HDL, it can pick up cholesterol from peripheral tissue, such as those that are engulfed by macrophages, and eventually delivers the cholesterol back to the liver for degradation in the form of bile. So the return of the cholesterol to the liver is what we call reverse cholesterol transport. Let's take a look at the different stages now. So as I have mentioned earlier, HDL begins as an apolipoprotein A1. It is synthesized and released by liver and cholesterol. It is devoid of any lipids, and it is in the circulation that it will pick up cholesterol and become a nascent HDL particle. Now in circulation, it will also accumulate several apolipoproteins, which includes ApoC1, ApoC2, ApoD, E, F, M, and O, virtually the entire alphabet. As well as it will carry more than 100 antioxidant enzymes. So the pre-beta HDL eventually will interact with macrophages. Those macrophages contains receptors such as ABCA1. So it interacts with a macrophage by binding with and interacting with ABCA1 or ATP binding cassette protein A1. The transfer of cholesterol, however, from HDL, from macrophage to HDL is facilitated by another protein called ABCG1 or ATP binding cassette protein G1. Now the HDL is filled with a lot of cholesterol, and this cholesterol is ready to be transported back to the liver by a process called reverse cholesterol transport. Now, while transporting cholesterol in circulation in a mechanism called reverse cholesterol transport, the cholesterol will be esterified by HDL-associated enzyme called lecithin cholesterol acyl transferase that hydrolyzes the cholesterol, that esterifies the cholesterol, rendering it even more hydrophobic. Now, the cholesterol eventually interacts with scavenger receptor protein B1 found in the liver. So the HDL is never internalized, but rather this only transfers the cholesterol from HDL to the liver, where it is eventually catabolized in the form of bile. And HDL remains in circulation, continuing to pick up even more cholesterol. Now let's take a look at the relationship between HDL, LDL, and its precursors, IDL and VLDL. The two are actually connected by a protein called cholesterol ester transfer protein. And what is the function of this particular protein? It facilitates the exchange of cholesterol from HDL to any one of these following lipoprotein in exchange for triglyceride. In other words, when CETP is very active, it results in the lowering down of HDL and increase in the level of LDL. Unfortunately, trans fatty acid activates this particular enzyme. And as a consequence, excessive intake of trans fatty acid lowers HDL and increases LDL, putting you at risk for atherosclerosis. So what is now the level of HDL that a person or a patient should target? Well, there is a direct correlation between HDL level and risk reduction in atherosclerosis and coronary heart disease. HDL above 50 milligram is less likely to experience coronary heart disease than individuals with levels below 40 milligram per DL. So in other words, the higher the level of HDL, the better it would be for a person's health. So the normal value is 40 to 50 milligram for men, whereas it is ranging from 50 to 60 milligram per DL for women. Just remember 50. In HDL, the value that you should remember is 50, whereas for LDL, the value that you should remember is 100. Anything less than 50 would put the patient at risk for coronary heart disease. And anything higher than 50 or greater than 60 is associated with some levels of protection against heart disease. Let's end this particular review with a summary of what we have discussed. Chylomicron transports exogenous dietary lipids. VLDL transports endogenous hepatic lipids to peripheral tissue. LDL transports cholesterol from hepatic to peripheral tissue. And finally, HDL is responsible for reverse cholesterol transport. We shall continue with the rest of the lecture and review in the following videos.